Good.
Okay, so this is a filler talk. Jake McQuinn was supposed to be here to give this, but I think due to unforeseen circumstances, he just started a new job and wasn't able to come. Jacob was going to be our main representative from kind of the Julia data community, but we hope that he'll be able to deliver his talk maybe online in a different way in the future. So just keeping with the theme of kind of what we've heard this morning, I was going to go in and talk about my experience with chunks from a biomedical perspective, and maybe a little bit lower level perspective. What I've done is adapt to kind of a more general talk to kind of tie in with everything we just heard. So, and you can cut me off in about 20 minutes.
Okay.
My slides are moving themselves. Okay, so just a little bit about me. I've been trained as a biologist. Most of my time has been spent training at medical schools, doing kind of biomedicine, mainly more basic biology. Where I've ended up is the Howard Hughes Medical Institute research campus. And maybe our biggest thing there is different kinds of microscopy, namely light microscopy and electron microscopy. And so and for us, our challenges there have been kind of, we make the instruments that actually collect the data. And so part of our frustration has been trying to figure out how do we deal with file formats to get the data in the right place at the right time, and so we can efficiently access it. Which is actually a little bit of a frustrating problem because you could solve some scientific data problems, but it's all your responsibility. And often our vendors don't cooperate as well as we would like them to. Kind of what I do with that is I take, let's see if that's going to play. Okay, so basically I take raster data that we just heard about, usually 4-dimensional 3D spatial data plus over time, and then use that to model, in this case, C. elegans, a kind of worm. And so there's a lot of processing that went into this. I'm not going to talk about this, but basically I'm just trying to explain kind of what my perspective is as a biologist. Okay, I might just need to speak into it. Okay. So, so mainly what I want to talk about is kind of chunks. Last year at JuliaCon 2023, I mainly talked about HDF5 JL. And I'm going to talk a little bit about that and a little bit about Zarr and how we can maybe try to put this all together. So earlier this morning, I'm not sure if we really got into kind of this abstract concept of why we're doing chunking, other than maybe wanting to more locally access data or access large data sets out of core. So I'm going to cover some of that initially. Let's talk a little bit about differences between kind of where these chunks are actually stored, and again to some details about what I've been struggling with HDF5, and also how this kind of starting to converge with, say, Zarr v3 and sharding. I think there's been kind of some evolution in terms of scientific file formats lately. We moved Zarr and these newer file formats have been trying to distribute chunks over many files or objects, as they may be. And so that is very convenient in that we can immediately find the data that we want to look at without having to kind of parse a bunch of metadata. But the problem that I've encountered here, and I think everyone who's worked with Zarr, is that these are very hard to move around a disk or your cluster, or you have to deal with some very different kind of mechanisms to move them around cloud storage. And so there's kind of this trade-off here. More lately, some of these schemes have started to implement shards, which are basically super chunks that have smaller chunks within them. But to me, this seems like going around in a circle. First, we took individual chunks, broke them apart into individually addressable files, but now we're putting all the chunks back together and it's starting to look more like NetCDF or HDF5, which is where we started in the first place. And so it sounds like we're going in a circle. So what's going on here? Although I think one advantage here is that There's some potential for maybe reading multiple chunks at a time, if they're sequenced in a certain way, if there's maybe they implement some kind of space filling Morton Z curve. And so there's potential for further optimizations there, which is kind of what I was asking Fabian about earlier in terms of do we need another interface to kind of make a second order abstraction. And so I think I probably covered a little bit about this in the last slide, but there are some problems with trying to abuse a file system to be your local key value store. File system is doing a lot more than just identifying where data is. You have all kinds of ownership and permission issues, especially if you're on like a Windows-based system where most of my devices, acquisition devices run. Windows particularly has high latency per file access. I think I measured the stat calls are about 100 times slower on Windows than they are on Linux. And I don't really have a choice where microscope manufacturers implement their drivers and software. So that's been very frustrating. Something that happens that, especially on Windows, you have to make separate API calls to access different files, and that can quickly add up when you have, say, 1 million files. Something that's nanoseconds versus microseconds quickly becomes seconds to minutes. And ultimately, you don't actually control well where the chunks are on disk. And so you can't really do a lot of optimization in terms of reading multiple chunks at a time. On the other hand, if we try to put all the chunks together, then we need to figure out how to locate them in that file. And this is kind of the whole problem that something like HDF5 was supposed to solve. There was supposed to be, this was supposed to give us a standard way to organize a file in a hierarchical fashion. So as Fabian talked, this is basic. This is a slide before. I knew I was talking after disk race, but basically we need an interface to access chunks, and I think maybe we already just heard it this morning. But I think there's also kind of front-end access, like how much is the user supposed to know that there's chunks, and how would that change algorithms that use these? Or do we put this more behind in a low-level access way, and perhaps we have two different interfaces to access chunk data? So there's been some differences now that support things like Zarr, in that we now have these key value object stores, which look kind of like file systems, but really are not. They basically get away from some of these per file permission issues by creating buckets for authentication. They have keys that look kind of like files in directories, but are really just a flat space. But there is something kind of interesting in the implementation of these cloud key value stores, in that they just use regular HTTP, and there's this potential for accessing parts of files over a request. And we can just take a look at that. This is just a normal HTTP request. And part of the thing that I really want to point out here is that there is this range parameter. And so what this allows us to do is ask a remote web server for a specific range of bytes. And so now this is starting to kind of get into, well, if we knew where the chunk was inside of a larger shard or larger file, then we could just retrieve it almost as efficiently as if each chunk were in separate keys or separate objects. Okay. And so bring that all back around, I started to think, okay, well, how about HDF5, which is the file format that underlines netCTF? And what is keeping HDF5 from being an efficient data store? Why did we have to come up with Zarr to get around problems that we were having with HDF5? And kind of looking at it and looking at interfaces for there were several ways to kind of get to chunks. And for the most part, HDF5 just prevents a high-level interface. It doesn't want you to think about the chunks underneath. You have to actually go through quite a bit of of hoops to kind of get it to tell you what's happening or where the data even is in the file. It just wants you to directly index into array. But so there's these several legacy functions here. And more recently, they introduced interfaces that allow you to actually read things at the chunk level, although it almost seems a little begrudgingly done. But if we look at that, basically these interfaces do give us kind of offsets into the file. And so that looks kind of promising. It looks like we should be able to receive raw chunked data. But I think part of the problem here is that the way the HDF5 library is oriented is that it usually requires us to do what's on the left side. It goes through the whole pipeline for us and doesn't let us think about what's happening at a lower level, or basically how the file's organized. Whereas Zarr is completely different, right? It basically doesn't do any of this pipeline for you automatically. It's really just this file specification or object source specification. And we really just want to be able to directly access chunks on the disk. And part of this is also kind of some of the underlying thinking of how things were going to be organized. They really went deep into B trees, and this makes the HDF5 metadata complex. Got ahead of myself there. This makes some of the HDF5 metadata a little bit more complex than you would think it should be. And so after kind of doing a deep dive into the C library, something I found out is there are more efficient ways to access chunk data within HDF5, where I want to get information on where all the chunks are. And basically, HDF5 has two kinds of APIs. One is to get information on individual objects, but this is very slow because every time you ask for the nth object, it does a search through its metadata to try to do that, and that becomes very inefficient. Whereas what we really want is the iterator. We want to be able to maybe go through and possibly get all the chunks that exist, instead of restarting a search every single time we ask for the nth chunk. And so it turned out that it existed eternally for HDF5, but they weren't exposing it. So I found someone else actually found this and basically did a bunch of work to push this all the way through to now expose this as a public interface. The only problem is that for the Python folks, this is really, really intimidating because it requires you to pass in a callback function. For Julia, this is a little bit easier. We could create a C function that could act as a callback, and so we could use these iterators. And it turns out that this solved like a huge problem of scaling that I was encountering, because as I mentioned, there were all these older legacy functions that allowed you to access this chunk information, but if you scaled up to about 60,000 chunks, this would be incredibly slow. But now with chunk iter, this is much faster. You have linear scaling. And just kind of looking at benchmarks as what were the access times with this, you can see that basically we're not. This is an exponential plot, sorry, a logarithmic scale on the y-axis. That basically now we have much better scaling as the number of chunks grow. And it turns out basically this was now really important. It solved a lot of problems with how other people were having with accessing chunks in HDF5 files. I worked a little bit with some of the BLOS folks to kind of make this fast, and so now PyTables has implemented this as an accelerated method for getting data out of HDF5. In HDF5JL, I implemented this as a kind of surface function, get chunk info all, as opposed to just get chunk info. So this allows you to kind of retrieve the entire vector of chunk info, which will tell you where all the chunks are within the HDF5 file. And now if you think about that, combining all that together, if we now know where all the chunks are in the HDF file, then we can completely forget about HDF5. We can just go into the HDF file, access a certain byte offset, and retrieve the chunks, just like perhaps we're using for Zarr. Now, strangely, Zarr started going back the other direction, which is they started thinking about how do we take a bunch of chunks and reduce the number of files for whatever reason, and now put them back into one big file, which sounds a lot like HDF5. And it's a little bit frustrating to watch because I think it wasn't clear that the people writing this had really studied HDF5, and so it looked like they were starting to make the same mistakes over again. But eventually they came up with a fairly simple format, which is you could just append to the end of a file where the chunks are. I thought that was pretty good, but it was missing one critical thing that HDF5 did have, which is right at the end they have a checksum to maintain the integrity of the data. Because if your chunk index gets screwed up, or maybe it's not what you think it is, then you can't read it at all. And so kind of after working with them, I tried to make it a little bit more similar to HDF5. We added the CRC32 checksum. And this thing actually looks like almost identical to an HDF5 data structure. But now this has been implemented in Zarr v3 as the sharding codec. And so now this is now available. So now I think we're basically getting to the point where the HDF5 and Zarr v3 interfaces are starting to look really similar. I know how to get the chunk indexes, offsets, and sizes for both these. And now perhaps we could just write a general thing that could read either HDF5 or Zarr. But what happens? Sorry, my touchpad's really sensitive. But what happens if we could just use them at the same time? What happens if we could have a Zarr shard that could be simultaneously an HDF5 file and a Zarr shard? And it turns out that's possible. It depends how crazy you want to be. As I mentioned, the shard trailer is actually pretty similar to the HDF5 structure. So we could actually have HDF5 and Zarr share the same data structure. The only difference is I need to teach Zarr a slightly different checksum codec. For some reason, the HDF5 went with something called Jenkins lookup 3 function instead of CRC32. But that said, we do have a Julia implementation of this weird checksum function, so it's not a huge problem for us. It's in JLD2 at the moment. And so you could think of basically a file that looks like this. We have a little bit of HDF5 header that just points at maybe where the chunk metadata is, could be at the bottom. And then basically we have the Zarr shard trailer right at the bottom of the file. And this is perfectly compatible. Both HDF5 and Zarr are perfectly happy. And so we're starting to get convergence of these two things. Okay, so I looked at this and I was thinking about, okay, there's one other thing that I think a lot of microscopists fight me with about is like, why don't I just produce TIFF files? Well, I looked at TIFF a little bit, and actually, I think we could actually have a file that's simultaneously a TIFF file, an HDF file, and possibly a Zarr shard, which would be, I think, fantastic because now everyone could read it however they would like. The reason this is possible is that HDF5 has a mechanism to offset its header data at 2 to the n bytes after 512 bytes. So you can put it at 1 kilobyte, 2 kilobytes, et cetera. And all TIFF requires is a few bytes at the very beginning that points to image file directory metadata. Now, the one problem is that TIFF usually doesn't deal with 3-dimensional data, but that I usually end up collecting through a light sheet microscope, or rather my colleagues collect. But it turns out there is some obscure TIFF tag for encoding tiled depth. And so it's very possible that we could actually have even volumetric data shared between TIFF, HDF5, and Zarr shards if people can recognize this additional TIFF tag. So I think in summary, I think this solves a particular problem that I have with scientific data, in that there's a proliferation of file formats. Everyone seems to come up with their own, and more so, different fields don't really communicate very well, and end up re-implementing very similar ideas over and over again. I think if one kind of is able to look between fields, and I think Julia is actually a great language for exploring this stuff. It's been great to kind of go between different file formats, different interfaces, to be able to kind of interrogate how this works. Okay, So I think I'll finish there. Um, basically, we've been using Zarr because there's some advantages to having one file per shard. It's very simple. It allows you to access individual objects. But this very much depends on the underlying source system, especially if it's a Windows file system. Um, but now we've implemented very efficient direct chunk access that we can access from Julia. Um, and maybe this is actually mappable to the same kind of concept with Zarr shards. And so I think we have an opportunity here to converge multiple paths here and possibly kind of just create a single interface that can maybe handle everything. And so I think the main reason that I haven't implemented this arrays is because I've been trying to solve this problem with HDF5. I've done it now. It required writing some C, but it's done. And so I think we're just about to do that. So thank you, and take any questions.
Okay, so other questions? If not, I would have many, but the first one would be, how do you think your work relates to what the care chunk people are doing? I mean, like, because that's really a very similar approach by basically, they basically build catalogs of like all the chunk positions inside HDF5 files and index them and then access them as if they were at Zarr. I mean, like, so how do you think about that?
Right. So Circular Chunk is a Python library that basically tries to generalize over chunk interfaces. I think it is related in that it has the same goal of trying to extract out common chunk information, but usually as a separate file, as kind of an accessory file. Whereas what I'm doing is trying to actually not have these accessory files because that seems rather fragile to me and things will quickly get out of sync. And so in my case, I've been trying to implement it as part of one file. But I think it's very related. I think I have code in Chunk as well, basically as I've discovered how to make these things more efficient. And so they're also using that same method to efficiently extract chunk information from HDF5 now. Although now it's so fast that you don't necessarily need to do that. It's a kind of discrete stuff.
With all the technical challenges, how much thought or experiments have you done with API ideas for using the chunks?
I haven't really, right? I was just trying to get it to the point where for common file formats that were before me that I could efficiently access it. And I was hoping Fabian's exploration of disk arrays would take care of the API side. Although I do see a little bit of problem with maybe the sharding potentially because there could be some advantage for like pulling a whole shard down and keeping that cached. But I think it could also possibly be kind of a nested disk array implementation. But those are hypotheses that I have at the moment. So.
Yeah. Okay. Are there more questions? Okay, then let's thank Mark.